So I think let's just go ahead and get it started. It is my great pleasure to introduce today's CRML distinguished lecturer, Jenn. Jenn is a senior principal researcher at Microsoft Research in New York City. She's a part of the FATE group, which is quite famous for research on fairness, accountability, transparency, and ethics. And her background is in machine learning and algorithmic economics. And before coming to Microsoft Research, she was a professor at UCLA, where she also got the NS of Korea and Presidential Early Career Award. Before that, she's also graduated with her PhD from UPenn. And she has a very impressive portfolio of published papers in the area of FATE and also machine learning and related area. And I just saw that she's going to be the program co-chair for NeurIPS this year. So I don't know if I should congratulate, but it's definitely a very, I think very impressive contribution to the machine learning community. So with all that, I will give the floor to Jenn, and please join me in welcome Jenn virtually to UCSB.
Great, thank you so much. Let me just share my screen here. Give me a moment. Oh, that is not what I meant to press. Give me one more moment here. Okay, can you see my slides? Great, fantastic. Always good when things work. Great, so yes, so I'm Jenn Wortman Vaughan. I am very excited to be here today, so thank you so much for inviting me. Today, I'm going to be talking to you about my work on intelligibility throughout the machine learning lifecycle. And throughout this talk, I'm going to be arguing for the importance of taking a human-centered view of machine learning. So I don't know about all of you, but I have been going to all of these virtual talks, and quite frankly, I find them very exhausting, both as a participant and a speaker. And I tend to find it much more difficult to connect with the audience when we're not all together in the same room. So one thing that I've been trying out these days when I give talks is trying to just start with a little bit of a backstory on my own research interests and how it is that I came to be interested in the topics that I'm going to be talking about today. So let me tell you a little bit about that. My research training initially was in two areas, so machine learning theory and algorithmic economics. And what this basically means is that in my past research life, I spent most of my time designing algorithms and proving formal mathematical guarantees about these algorithms. And I still spend some of my time doing that today. But these days, I spend more of my time on human-centered approaches to transparency, intelligibility, fairness, and responsible AI more broadly. So a lot of people hear this, and quite naturally, they ask me, how did that happen? That is a pretty big switch. I can basically trace my interest in these topics back to 2016. So in 2016, I went to Washington, D.C. to attend one of these panels on AI and society that are happening all the time now. And at this panel, one of the panelists made this bold claim that soon our AI systems will be so good that all of the uncertainty will be taken out of our decision-making. Now, to me, this was just an utterly horrifying thing to hear, right? We all know that the world is full of uncertainty. All of our AI systems and all of our machine learning models are going to have uncertainty baked into them, whether it's explicit or not. And I just found it completely irresponsible to tell people that AI could somehow magically take this uncertainty away. So I came back to New York after this, kind of fuming about it. And I immediately ranted about this to my colleague and good friend, Hannah Wallach. And Hannah and I spent a lot of time over the next month or two just constantly dissecting this claim and trying to figure out why it is that this bothered us so much. Now, just to give you a little context, this was 2016, so right around the time that there started to be all of this talk about democratizing AI and making it easy for people to build and deploy machine learning systems on their own. It was also right around the time that in the US, Hillary Clinton's chance of winning the election was hovering around 80%. And basically the general public was treating this like a done deal. So, watching all of this play out, all of these current events, and replaying this panelist's quote over and over in my mind, I became just obsessed with this question of how well people really understand the predictions that are coming out of models. Now, as a machine learning theorist by training, I was always trained to state my assumptions really clearly and explicitly. And the stating of assumptions was kind of core to what I do. And I became afraid that people may not always understand the assumptions that go into a model or the implications of the assumptions that go into a model, or they might not understand the uncertainty that is behind any prediction. So these worries led me to discover this literature that was coming out of the machine learning community on intelligible or interpretable machine learning. People use these terms slightly differently, but for the purpose of this talk, I'm just going to use these interchangeably. Now, I saw this literature and I got really hung up on the fact that people were designing all of these methods without stopping to define exactly what it is they mean by interpretability or intelligibility. So basically proposing these solutions without first stopping to define the problem that they were trying to solve. So I started talking about this with colleagues of mine at MSR with backgrounds in psychology and HCI and other human-centered fields. So people who know about behavioral experiments and user studies and so on. And with these collaborators of mine, I started running my own experiments to see how interpretability plays out in practice. And I ended up just getting really excited about this area. And over the past 3 or 4 years, this has become really a major theme of my research. And this is what I'm going to be talking to you about today. Okay. So I've said that we should take this human-centered perspective or approach to intelligibility. Why should we do that? Well, if you think about, the way that we often picture machine learning, and actually the way that we often teach machine learning in classes, we usually think about it as this fully automated process, right? We take some data, we use it to learn a model, and then out come these predictions. But more realistically, people are at the heart of the machine learning lifecycle, right? It's people who define the task that machine learning is going to be used to solve. People decide which data to collect. They decide how to clean and pre-process that data, how to label the data. And this data itself is often generated by people, either explicitly through for example, through crowdsourcing, or implicitly. So for example, if we have data containing images of people or text that people have written. People then determine which model to use. So should we use a neural network, a random forest, a linear model, something else? People choose how to train this model, how to test it, which may then require gathering data from additional people. People make choices about whether, where, and how to deploy a model. And of course, these models, once they're deployed, end up impacting other people's lives, often in these high stakes domains like medicine or finance. And finally, feedback from people is incorporated as the model evolves. So given the central role that people play in the machine learning lifecycle, I take the position in my work that building machine learning systems that are reliable, trustworthy, and fair requires relevant stakeholders to have at least some basic understanding of how they work. So this is roughly intelligibility. And there are a whole bunch of different stakeholders of machine learning systems out there that can benefit from this intelligibility. So let me just give you a couple of examples. So first, intelligibility can improve the robustness of AI systems by making it easier for data scientists to identify and fix bugs. This is a very common use case for intelligibility that we think about at Microsoft. Intelligibility can help doctors or CEOs or other decision makers decide whether they should trust an AI system and how much they should trust the AI system, ultimately leading them to make better decisions. Intelligibility allows designers to reason about how a system or a model works, and this in turn helps designers convey this information to end users. Intelligibility around characteristics of training data can help uncover potential sources of bias or unfairness in a model. Intelligibility can help demonstrate that you're complying with the regulatory obligations. It can enable new tools that help scientists who are developing models to make hypotheses about their world. So kind of knowledge discovery. And just more generally, intelligibility leads to more usable products when we're building with machine learning. Okay, so there are two main approaches to intelligibility that are often seen in the literature coming out of the machine learning community, okay? So the first type of approach is to design and deploy transparent or so-called glass box models that are intuitively simple. So simple here might mean something like a small decision tree or a sparse linear model. As one example, my colleague Dan Goldstein and his collaborators have some really nice work on simple point systems that a decision maker, so for example, a judge, can memorize and apply on the fly without even needing a pencil and paper for calculations. They show in their work that actually in many high-stakes domains, particularly when you're dealing with tabular data, these point systems can be nearly as accurate as more complex models like neural networks. As another example, my colleague Rich Caruana has a body of work on generalized additive models, or GAMs, that falls into the same category. The reason that GAMs are nice is that predictions have an additive structure which allows you to easily visualize the impact of a single feature on a prediction, right? So you have one function that corresponds to each feature and you can visualize that function. I'm going to come back to GAMs a little bit later in this talk. Okay, the second common approach is to design simple post hoc explanations for complex models. So you may have heard of LIME or SHAP, and I would put those into this category. Now, many of these approaches work by approximating a complex function using some sort of simple local approximation like a linear function that can be easily explained. And SHAP, which I'll also come back to a bit later in this talk, builds on ideas from cooperative game theory to assign an importance to each feature, which is intuitively some measure of how much the feature contributes to a particular prediction. Okay, but despite all of this really cool research that's going on, there's still actually a fair amount of disagreement in the machine learning community about what intelligibility means and how to measure it. So looking at all of these proposed approaches that I mentioned, it's natural to ask, what makes a model or an explanation simple? How is simplicity actually related to intelligibility? And do these models or these post hoc explanation techniques actually help users achieve their goals? There have been a couple of position papers examining these issues over the last few years. And as Finale Joshi Velez and Bean Kim nicely pointed out in theirs, The machine learning community often has this "you'll know it when you see it" attitude towards intelligibility or interpretability. Now, the difficulty of defining and quantifying intelligibility is compounded by the fact that there are different types of users or different types of stakeholders. And these users have different needs in different scenarios. So the approach that works best for a CEO who's making strategic decisions is likely to be different than the approach that works best for a regulator who needs to understand why a particular individual was denied a loan. And this in turn is probably different from what works best for a data scientist who's trying to debug a model. Additionally, all of these approaches that I've mentioned so far have focused on intelligibility of the model itself. But this, if you think about it, this is just really one piece of the picture in this kind of bigger machine learning life cycle that I showed you earlier, right? And depending on who our stakeholders are and what goals these stakeholders have, we may want to introduce intelligibility at other stages of the machine learning life cycle as well, starting from the definition of the problem being solved and the data collected all the way through to model deployment. So these concerns have prompted me in my work to adopt a human-centered agenda for intelligible machine learning. Now, within the FATE research group at MSR, we've been working on this agenda from several angles. So first, we propose that people stop relying on intuition and instead empirically test which factors of a model enable users to better achieve their goals. And in a few moments, I'll tell you about some work we have in this space that examines how factors that are commonly thought to influence the intelligibility of a machine learning model actually impact people's use of the model. A second approach is to consider intelligibility beyond the model. So, for example, intelligibility of data or intelligibility of objectives or performance metrics. Here, I'll tell you about a couple of pieces of work that we have in this space. Work on data documentation and work examining how the stated and observed accuracy of a model impacts people's trust. Finally, we propose that people design and evaluate methods for achieving intelligibility in context with relevant stakeholders. And here I'll tell you about some more recent work examining how data scientists perceive and use intelligibility tools. I should mention that my colleague Hannah Wallach and I have recently written a book chapter covering this agenda, and you can find that on my website. So if you're generally interested in this, I would encourage you to check that out. So let's see, before I jump into this first point, I'm going to pause for a moment just to double check if there are any questions so far. I can't actually see any of the moderators, but I'm going to assume we're good to go. Okay. I will keep going, but I'm happy to take questions along the way if people have them. Okay, so let me jump right into this first point. Okay, to question our intuition on intelligibility and empirically test this intuition, my colleagues and I have found it helpful to think about intelligibility as a latent property that can be influenced by different manipulable factors. So things like the number of features in a model, whether the model is linear, the user interface, things like this. And that then impacts different measurable outcomes. So things like a user's trust, or a user's ability to debug the model, or a user's ability to simulate a model's prediction. Now, notice that all of these properties on the left are properties of the system design. So, properties of the machine learning system. Whereas on the right, we have properties of human behavior. Now, taking a cue from psychology, in a project that was led by Farouk Poursabzi-Sengda and that will appear in CHI 2021 in a couple of months, we designed randomized human subject experiments to isolate and measure the impact of different system factors on the fundamental properties of human behavior that are relevant to intelligibility. So the idea is to randomly vary these types of system factors that I have on the left, and then measure the impact on the types of human properties that I have on the right. And while this may seem simple, it's actually really hard to do this in practice while holding everything else equal. Okay, so in our experiments, participants were asked to make predictions about the selling price of different apartments with the help of a model. So in addition to a simple baseline in which participants did not have access to any model, we considered 4 randomized experimental conditions in a 2x2 design, corresponding to the 4 models that you see here. Now, I don't expect you to be able to read everything on the screen, but let me point out the differences between these conditions, okay? So first, the models on the top use 2 features, while the models on the bottom use all 8. Second, the models on the left are black box, while on the right, you see a transparent linear regression model with weights visible to the participants. For these conditions on the right, we did explain during a training phase exactly how these models work so that participants could get to understand this. Now, crucially, in all of these conditions, participants see the same model input. That is, all participants see the same apartment features and the same model outputs or predictions. So that is, we specifically chose apartments where the 2-feature and 8-feature regression models make the same predictions when rounded. So the only difference between these conditions is what people see in between. And this means that if we observe any differences between conditions in terms of participants' behavior, we can safely attribute those differences to the differences in the model, right? This is super important to our design. Okay, so I'm not going to go through our studies in detail because I want to get through a lot today, but let me mention a couple of key results and implications, and I'll point you at the paper if you're interested to learn more. Okay, so first, we found that participants who were shown a clear, transparent model with a small number of features were best able to simulate the model's predictions. So this is perhaps unsurprising, but it's reassuring to see in the data. It means that participants did actually understand this 2-feature regression model. However, we found no improvements in the degree to which participants followed the model's prediction on a typical example, when it generally would have actually been beneficial for them to do so. So in general, the model was better than the humans at predicting selling prices. So it would have been better to follow the model, but we saw really no differences here. Additionally, we found that in some cases, too much transparency can actually be harmful. So specifically, transparency reduced people's ability to detect when the model made a sizable mistake and correct for it. And we have some evidence that this is because of information overload. Now, this was something that was actually really surprising to us because it's kind of contrary from the intuition in the literature that more transparency is better. And more generally, these results just emphasize the importance of user testing and experimentation over just relying on intuition when designing and evaluating intelligible models. Okay. Before I move on, let me just pause one more time in case there are questions.
Yes, so there are 2 questions, both from Ivan Bekovich. So one question is probably related to the earlier part. So to what degree do you think intelligibility will become regulated requirement for an industry using machine learning? So this is the first question.
That's a good question. So My sense on this, and here, when I talk about regulations, I want to make it very clear I'm speaking for myself and not for Microsoft as a company. My opinion here is that we might see regulations in the future in specific domains, but likely not for just machine learning models in general. And we already, you can already kind of imagine what this would look like, right? There are some domains like housing and lending and things like this where there already are strong regulations just generally about the use of models. Finance is another one. And I could imagine that it would make sense to have domain-specific regulations in these domains. But one of the points that I just want to emphasize throughout this work is that approaches to intelligibility and how well they work are just so dependent on who the stakeholder is and what their goals are and what they're trying to do. That I can't imagine it would be a good idea to try to come up with some sort of regulation that applies like super broadly.
Thank you. Thank you. The second question is more related to the second part. It's also a great question. So Ivan was asking if there were unavoidable trade-offs between intelligibility and accuracy. Do you think there are scenarios where intelligibility will prevail?
Yes. So it's also a good question. So as I mentioned, or kind of briefly alluded to earlier, there have been some studies like this one that my colleague Dan Goldstein was involved in, where they looked at data from several domains in cases where they had tabular data specifically, so kind of feature values. And in many of these domains, they found that there was not, in fact, really a trade-off between intelligibility and accuracy, in the sense that quite simple models could do basically as well as neural networks in these domains. I think there will be other domains where this is not the case, and in particular, computer vision or speech or things like this are domains where you really do need more powerful models. But in those cases, maybe it isn't as important to have the same level of intelligibility. But I think in general, yes, there is probably some amount of trade-off there, but I think the trade-off is exaggerated a lot of the time.
Thank you. Thank you. One more question, and then we'll move on. So there's also a very related question is on transparency. So for transparency, let me rephrase this question. Is it always the case that, more transparency would be beneficial, right? Will there be cases that, for example, transparency could be harmful, right? How do we, balance transparency?
Yeah, so I definitely do not think that transparency is always beneficial. I guess it depends here exactly what you mean by transparency also. So if you're talking about transparency in the sense of that, I was just using it in the previous part of my talk. So kind of actually making the model internals transparent so that your stakeholders can see the model internals, then even in this experiment I was just talking about, we are finding that that was not beneficial. That was causing people to actually have worse performance in correcting mistakes that the model made. There are other cases where it might be harmful as well. Cases where there are concerns about models being manipulated. Some cases where there are concerns about kind of trade secrets or proprietary information in models. But I guess in general, I think that intelligibility usually is a good thing.
Thank you, Jenn. So I suggest we continue, and then we're gonna go over all of the questions in Q&A towards the later part.
Sounds great. These are good questions. I'm excited for the Q&A. Okay, oops, I went too fast. Great, so let's move on to the second direction, which is intelligibility beyond the model. Okay, so as a first example, A couple of years ago, a group of us at Microsoft Research in New York started a project called Datasheets for Datasets. Now, inspired by datasheets for electronic components, we propose that every dataset be accompanied by a datasheet that documents relevant information about its creation, its limitations, its intended uses, and so on. Now, I happen to be somebody who personally gets very excited about documentation, but I know that not everybody out there in the audience will share this passion with me. But I would argue that documentation is actually critically important, right? So datasheets can help dataset creators uncover possible sources of bias in their data or unintentional assumptions that they might have made. They can help dataset consumers figure out whether a dataset is right for their particular needs, if they're deciding whether they should use a dataset to, say, train or evaluate a model. And if you expose a datasheet either in whole or in part to end users, they can help these end users figure out how much to trust a system that's been trained on data. So we've been piloting datasheets across Microsoft and updating our proposal based on pilot results. And we've now got this proposal with questions on motivation for the data set, its composition, the collection process, any pre-processing or cleaning or labeling of the data, intended uses of the data, dataset distribution, and dataset maintenance. We've also got questions about ethical and legal considerations that are kind of sprinkled throughout. And we've constructed a proposed workflow so that each of these sets of questions can be answered at a different phase of the dataset's lifecycle. So there are actually a number of research challenges that have come up during these pilot studies. Some are to do with the questions that we ask. So for example, how should you think about these questions and modify them when a data set contains streaming data instead of static data? There's also a lot of questions around workflows or incentives. And one thing that we've definitely learned here is that there's not going to be a one-size-fits-all solution. But given the central role that data plays in machine learning, I think the payoff for getting this right is potentially huge. Now, I wanted to mention this today because one way that you all can actually get involved is to try to create your own data sheets when you release data sets online. And we've actually started seeing some awesome examples of researchers including a data sheet as part of a paper, either in an appendix on a paper or through a separate link. And I would love to see this become a community standard. So I just want to mention this and you can kind of help us make that happen. Okay, as a second and extremely different example of intelligibility beyond the model, let me mention some work of ours that was led by Ming Yin, who's now at Purdue, that received a Best Paper Honorable Mention at CHI in 2019. And this work can be viewed as a study of intelligibility of performance metrics. Okay? So in this study, we set out to examine first whether a model's stated accuracy on held out data affects people's trust in the model. If so, whether it continues to do so after people have observed the model's accuracy in practice. And finally, how a model's observed accuracy in practice affects people's trust. To do this, we again made use of randomized human subject experiments. We showed subjects information about pairs of people who had been matched through a speed dating event. So subjects were first asked to make their own predictions about whether a speed dating participant wanted to see his or her partner again. They were then shown a prediction from the model, and finally they were given a chance to revise their original prediction. So they did this many times, completing 40 such tasks in 2 phases. So at the very beginning of the first phase, we gave them information about the model's accuracy on held out data. Then, after the first phase, so midway through, we gave them feedback on how they themselves had performed so far, so what was their own accuracy, and how the model had performed so far. What was the model's accuracy on these 20 examples? And at the end, we had them answer a few questions about their use of the model. In each of these experiments, we varied either the stated accuracy, so what we're telling them at the beginning, or their observed accuracy of the model and the feedback that they see in the middle, or both. So these were randomized conditions. Okay, again, I'm going to skip right to the high-level results and implications and point you at the paper if you want detail. So first, we found that the model's stated accuracy on held-out data does affect people's trust in the model, and specifically that they're more willing to depend on the model when its stated accuracy is higher, which is reassuring. This is one of those results that may sound obvious in retrospect, but actually hadn't been studied in the literature. We also found that people put substantial weight on their own interactions with the model and on the accuracy that they observe. We saw this happen even though subjects had a somewhat limited interaction with the model. That is, they changed their behavior after getting information about how the model performed in the first phase, even though this first phase was only 20 tasks. And these and other results in the paper, again, highlight these needs for designers of machine learning systems to just clearly and responsibly communicate their expectations about model performance. So we do see that this information shapes the extent to which people trust a model, both before and after they observe it in practice. And I think that there's kind of a huge open area for research here in how to kind of best communicate performance statistics about a model to users of this model in order to set their expectations appropriately. Okay. Before I move on to the final bullet here, I'll just see maybe if there are any questions specifically about what I've been talking about, we can take them and we can hold general questions for the end.
Right, yeah, so there were some questions that are pretty broad, so maybe we can save them towards the end.
Yeah. Great, let's save them and I'll just get through this last part here. Okay. Good. Oh, I'm getting ahead of myself again. Okay, moving on to this final bullet point here. I'm going to spend the next couple of minutes talking about some more recent research, looking at how we can evaluate the intelligibility of existing tools with stakeholders in context. And this is work that was led by an incredible summer intern, Harmon Cower, and that received a Best Paper Honorable Mention at CHI 2020. So in this work, we're zooming in specifically on data scientists building models as our stakeholders of interest. And in particular, we're interested in how data scientists perceive and use existing off-the-shelf intelligibility tools, what challenges they face using these tools, and what opportunities we have to make these tools better. So before I get into our study, I just want to take a step back and say a little bit about why this type of evaluation is challenging. And I want to be super clear here that the reason that this type of evaluation is often missing from machine learning papers on intelligibility is not because machine learning researchers are lazy or just don't care, but because getting this type of evaluation right is really a research agenda in its own. So first, it requires expertise in both the machine learning side and in HCI or psychology or other human factors. It requires knowledge of both the academic literature on machine learning and intelligibility, and also on day-to-day engineering practices of data scientists. It requires both a qualitative analysis to understand the nuances of the ways that these tools are used in practice, as well as quantitative methods if you want to scale up and have reliable findings. It should mimic a realistic data analysis setting, but not be too cumbersome. So in our case, we didn't want to keep these data scientists for more than about an hour for a study. So this is what I mean by too cumbersome here. And it requires separating effects of the model, the intelligibility technique, and the user interface of the specific tool, which can easily become conflated. So to address these challenges, first we recruited a diverse team to work on this project. So Harmon, the intern who led this project, brought all of the HCI expertise, but our team also included a couple of machine learning researchers like myself, as well as data scientists who have more practical experience building and working with their own intelligibility tools. We attempted as best as we were able to put the data scientists that we studied in a realistic context, and I will tell you more about that in a moment. And finally, we used a mix of qualitative and quantitative methods. So specifically, we started with some pilot interviews, which are meant to just identify challenges that were faced by data scientists in their day-to-day work. We then ran our main interview study to observe these data scientists interacting with an intelligibility tool and see what they do when they're faced with these challenges. And finally, we ran a large-scale survey to scale up these results. So again, our goal was to evaluate data scientists' ability to use existing intelligibility tools to address day-to-day challenges that they face. So our first step had to be actually understanding these types of challenges that data scientists face in practice, or the contexts in which they'll use these intelligibility tools. And this was the goal of our pilot interviews. So from these pilot interviews, we identified 6 common challenges, and I'll come back to these in a moment. Building on these challenges, we designed an interview study in which participants were put into context, in this case, working with real data, a real model, and a real intelligibility tool. And here we wanted to explore both of the types of tools that I mentioned towards the start of this talk, both these simple Glassbox models and post-hoc explanations. So we had half of our participants use generalized additive models, GAMs, and half of them use SHAP, this post-hoc explanation technique. We began with a pre-study interview about participants' prior experience and expertise before moving on to the main study, and ended with some follow-up questions. For the main study, participants were given a Jupyter notebook that was already set up for them. So they first saw a tutorial on the intelligibility tool they were given, which was based on existing published documentation with a bit more detail added in. Then they explored a trained model, seeing visualizations from the intelligibility tool. And after they did this, they answered some questions about the model, being able to refer back to the tool when they wanted. Okay, so each of these 2 tools I mentioned, GAMs and SHAP, provide 3 types of explanations. So the first is local feature importance, or a description of how important each feature is for a prediction that's made on a particular data point. The second is global feature importance. So how important is each feature on the whole across the entire data set? The third type of visualization zoomed in on the way that a specific feature, so in the example I'm showing here, age, impacts prediction. In the study, we used a modified version of the popular adult income dataset, which predicts whether a household earns more than a certain amount of money. Specifically, we modified this dataset to reflect the types of challenges that we extracted during the pilot study. So for example, data scientists often face problems due to missing values in the data and the way these missing values are filled in. So before training the model, for 10% of data points with positive labels, we removed the age value and used the common approach of replacing it with the mean across the rest of the data set, which in this case was 38. So this resulted in our model exhibiting this strange jump in predictions for 38-year-olds. As another example, to capture ad hoc categorization, we took one feature, the number of hours someone works in a week, and bin values into these somewhat nonsensical categories of 0 to 30 hours, 30 to 60 hours, 60 to 90, and 90 plus. So almost all data points were in the 30 to 60 hour bucket. Now, a couple of different themes emerged from a qualitative analysis of our interview data. So first, we found that there were a set of participants who overused these tools, using them to justify cases when the model exhibited strange behavior, right? So this led them to place too much trust in the underlying machine learning model. So as one participant who was given GAM said, age 38 seems to have the highest positive influence on income based on the plot. Not sure why, but I guess if that's what's shown, makes sense, right? Another participant who was given SHAP ran some tests on their own in the Jupyter notebook and was willing to accept the model's behavior when those tests agreed with SHAP's output. So these are both examples of overtrust. On the flip side, we also saw some cases in which participants underused the tools because they just weren't confident about exactly what these tools were showing them. Another theme that emerged was the importance of social context. So in particular, participants seemed willing to trust what the intelligibility tools were telling them simply because they were publicly available tools. And one participant said this quite explicitly, right? I guess this is a publicly available tool, must be doing something right. I think it makes sense. As another said, I didn't fully grasp what SHAP values were. This is a pretty popular tool, and I get the log odds concept in general. I figured they were showing SHAP values for a reason. Maybe it's easier to judge relationships using log odds instead of predicted value. Anyway, so it made sense, I suppose. Okay, so we thought these qualitative results were super interesting and also a bit worrisome based on the amount of overtrust we were seeing. But we wanted to scale up our findings, so we designed a survey to attempt to replicate this interview setting at a larger scale. So this survey began with some questions about demographics and experience. Since participants in the survey wouldn't be able to interact directly with the Jupyter notebook anymore, we then showed them screenshots of common ways that our interview participants had chosen to explore the dataset model and tools. And finally, we asked them a bunch of questions about the data set, model, and tool that they were supposed to answer based on screenshots of the visualizations that we showed them. So again, we were kind of trying to replicate this setting from our interview study, but in a way that we could do this at scale. We took advantage of having a larger pool of participants here to run some randomized controlled experiments as well. So we randomized two things. First, as before, we randomized whether each participant used generalized additive models or SHAP. And second, in order to understand how people were affected by the actual content of these explanations, we randomly showed half of our participants the normal version of global feature importance that the tool would output, while the other half we showed a manipulated version of global feature importance, in which we permuted the feature names so that less important features were shown as more important and vice versa. So our qualitative findings on the whole were pretty similar to what we saw in the interview study, though some additional themes emerged. So for example, even with the tutorials, few participants could actually describe the visualizations beyond just a superficial level. So beyond something like saying that they show feature importance, but they couldn't describe, what feature importance is. And participants use the visualizations to craft their own narratives about the data and convince themselves that the model was reasonable. So again, we're seeing that some participants seem to increase their trust in the underlying model just because they're being shown an explanation, even though I would hope that seeing this particular explanation would make them more suspicious about the model's behavior. So the explanation is showing them something suspicious, but it instead of kind of making them suspicious of the model, it's making them trust the model more. Just to highlight a couple of our quantitative findings here. First, participants had higher accuracy on multiple choice questions about the visualizations they saw using GAMS compared with participants who used SHAP. And the participants who used GAMS were also more confident about what they were seeing compared with those who used SHAP when we looked at self-reported confidence. In terms of these experiments with the manipulation that I mentioned, manipulating the feature importance values reduced participants' confidence that the explanations were reasonable, which is a good thing. The explanations were not reasonable. We had just randomly permuted the features. However, seeing these manipulated visualizations did not lead to any increased suspicion about the model or the intelligibility tool. So it made people, it kind of reduced their confidence the explanations were reasonable, but they still sort of went along with things and didn't raise any additional suspicions. So I think this work suggests several next steps for the community that I just want to highlight here. So first, we need more interaction between the machine learning community and HCI researchers. And we really need that interaction to happen earlier in the process, right? These human-centered approaches should be incorporated in the design and development of intelligibility tools from the start, in addition to just their evaluation, as we were doing here. And I have some kind of current work along those lines. Second, we need more tools that are designed to encourage deep thinking and discourage people from making snap judgments. So one of our study participants from this last study actually put it really nicely, saying there's this concept in UX called thinking fast and slow. While these visualizations are made to make me think fast, every detail about them requires that I think slow. And finally, in our study, as I mentioned, we had only about an hour of time from each participant. And I think generally the community needs more longer term studies to understand how people's understanding and usage of intelligibility tools changes over time with more exposure. Popping up a level, I've told you about a couple of studies that we've run on lay people, and this last study, which was run on data scientists, but there are many other stakeholders that I've mentioned who might require intelligibility. And a huge wide open direction for future work is to better understand the needs of these stakeholders and design approaches specifically to address them. And finally, as I've argued, we need to take a broader view of intelligibility and think about how to bring it to every stage of the machine learning lifecycle. So with that, I will close, and I'm happy to stick around and chat with you all and take additional questions. So thank you.
Thank you, Jenn, for the wonderful talk. There were a couple of very interesting questions raised during the talk, so let me go through them. And meanwhile, if there are any other additional questions, feel free to enter that in the Q&A function. So the first question is that, I really like the multi-stakeholder view, because normally we are not so clear about, what the users and stakeholders are. So that's really awesome figure. There's a question relating to that figure is about layperson, right? I think we spend a lot of time talking about data scientists and also how other people can use this. But for any reasonable complex data, Matt Howe has this question that, would it be difficult to explain machine learning rules to a layperson?
Yeah, so I think that we will certainly need different types of explanations for lay people, and they also will probably need different information than a data scientist would need, right? So, two of the studies that I was talking about were actually run on lay people. So at least to some extent, you know, we are looking at ways that lay people are able to understand parts of machine learning models and predictions that they're making. And I think it's going to be increasingly important in the future that we kind of think about how we can help lay people understand predictions from machine learning models, just because machine learning is being used in so many ways that impact people's lives now, right? Like it's commonly used in medicine, it's used in finance, it's used in, you know, in some cases in decisions about who's released on bail and who's not, and all of these things that are like really impacting people's lives. So even though there are extra challenges in trying to explain decisions to lay people, I think it's an important area. What information lay people need about a model might end up depending on the domain. So in particular, you know, you could imagine if you consider somebody who has just been rejected from getting a loan or something like this, maybe for them, the information that is most important to understand is not, you know, intricate details of how the machine learning model works, but something like which features of theirs that are actually in control are things that they should focus on if they want to make changes that will help them get a loan in the future. So maybe in this case, intelligibility might mean figuring out like how to convey actionable information to a layperson, right? In other cases, we really might want to help people understand more details of the model, but just it is super domain dependent.
Thank you. Second question is about the role of intelligibility, right? So what do you think about the role of intelligibility in the context of scientific research, reproducibility? So can you briefly comment on that?
The role of intelligibility and reproducibility. Yeah, so let me think about that for 1 second. So, okay, so I think that in terms of reproducibility, certainly there are aspects of transparency that come in, right? Like when we've been thinking about data sheets for data sets, you know, we had many motivations for data sheets, but one motivation that we discussed amongst ourselves was that these could aid in reproducibility in the sense that, you know, it's not always possible to release a full data set, especially if you're using proprietary data or something like this. But if you can release a data sheet that has enough information about how the data set was constructed and how the data set was cleaned and different properties, maybe demographic breakdowns, things like this, then you might be able to give someone else enough information that they can construct their own data set that has similar properties if they want to, you know, use that for reproducibility purposes or things like this. So I think it definitely comes up there.
Thank you, Jenn. This is very helpful. And
now I wanted to I wanted to chime in because I have a question that's very much related to the questions of reproducibility. First of all, excellent talk, Jenn. Really awesome work. So there was a like in the last couple of years there was a very interesting literature on so-called adaptive data analysis of preventing the kind of a p-hacking and false discovery in science and so on, which is a related problem to the reproducibility, but more on the like data abusing the data type. So say you are selecting the model based on the same data, and then you're fitting the data on the same model, and then you are somehow coming up with a hypothesis and test that, and you end up arriving at a result that's not actually statistically valid. So you can't reproduce if you collect a new data set from the same distribution. The interesting the interesting part about that literature is that a lot of the ideas that's developed over there is in some sense to hide information from the data analyst. So the data science are not allowed to do the same kind of data exploration, model building, and so on as before. In contrast, you have to say add noise to some of their queries, to their evaluations, and somehow to prevent information theoretically from such overfitting to happen. So I'm wondering whether there are some interesting connections between the intelligibility and the task of preventing p-hacking, and whether they could work together complementarily or they are at odds with each other.
Oh, that's a really interesting question, and not something that I had thought about in that way. I guess I often think about intelligibility in use cases where we kind of want to encourage as much exploration of the data as possible, which is usually the case when you are building real world applications. And a lot of the uses of intelligibility that we see by data scientists are specifically things where they're trying to use intelligibility techniques on a model to actually find like bugs in the data set, right? So, this example that I showed you that we kind of inserted into our study where we, removed a bunch of values of age and replaced them with the mean was based on something we were hearing from data scientists, but also the type of thing that we also see come up in practice all the time when people use these intelligibility tools. Like people use them specifically to find weird problems in the data. So that is all to say that yes, your question is kind of coming at things from a very different perspective than I'm used to thinking about, where you actually want to hide the data from people.
Yeah. They somehow model the data analyst to be an adversary who just want to overfit and to publish a Nature paper with some false findings, which is not really the case in practice, because scientists in reality wants to discover truths and to do the good things with the data. So yeah, I guess that's a very adversarial view of the data science. And I think like there might be some dimensions and angles where these two models can be combined somehow.
Yeah. I need to think about that more, but that's a really interesting question. By the way, just on this general subject, this is a bit of a tangent, but I'm not sure if I actually brought this up today when I was talking about this first project or actually this first two, actually all three of these projects where we were running randomized human subject experiments. But in all of this work, I've kind of taken up the practice that's now becoming more common in the psychology community of pre-registering hypotheses before we run experiments. So ahead of time, when we're designing these studies that I talked about, we might run a couple of little pilots, but before we collect any of the main data, we sit down and carefully think through all of the analysis that we're going to do and go to a website and kind of publicly commit to this analysis and commit to our hypotheses and all of this, and just register this in advance. And this is intended to avoid p-hacking because you register every detail and then you just do it and it works or it doesn't. And this is something that I would love to see catch on more in the machine learning community, because I do feel like, even though, as you were saying, I think most machine learning researchers or people who are looking at data come at it with good intentions, but there is some amount of something close to p-hacking going on, even in this unintentional way, where people do kind of take a data set, maybe try out a couple of different metrics, publish the ones that look good, try out a couple of different data sets, publish the ones that look good. And I would love to see some way that we can kind of take these practices from psychology and do something similar in the machine learning world.
I cannot agree more. Yeah, that's great practice. Yeah,
thank you. Okay, so let's continue the discussion. And I think there's actually one very timely question that's related to what Yuxiang just said, and also relates to our earlier discussion about transparency. So Professor Amar Al-Abadi has this question about trade-off between let's say transparency or intelligibility versus privacy, right? So what do you think, for these cases? Because sometimes for data and data sets, even metadata, right, or aggregate data, they can actually leak private information. So what do you think about this trade-off?
I mean, I think that trade-off does exist in some cases. I haven't done research in this area myself, so I don't have firsthand experience, but this does exist in some cases. I guess I would say kind of, the same type of thing that I just keep repeating because it's sort of like my mantra in this space, which is that, what you want to do is always going to depend on your domain and stakeholders. And in most cases, I don't think that there are privacy concerns that outweigh the benefits of intelligibility and transparency, but in some cases there might be. I do think that, I think you lose a lot by not being able to explore your data set and look at particular instances of the data, especially for the people who are building a model. So there is a bit of a loss there, but there's always going to be trade-offs.
Yes,
I haven't actually seen much work. I could imagine it's an interesting space to explore, like thinking about what what you can be transparent about and what you can't if you're aiming for privacy. But I haven't seen much work in that space.
Right. Before we go to the next question, I think this is really about one of the questions I wanted to ask, which is, I think for fairness, there were a lot of discussions in the past few years about the definition of fairness. There's individual fairness, there's group fairness, a lot of discussions. But I feel like for transparency, we don't have that much discussion about, what finer granularity we should be looking into for transparency. But I think during your talk and the QA, you briefly talk about, different types of transparency. So I'm just curious, if you have more thoughts about, fine-grained or quantifiable definitions for transparency, so how do you see we can go from where we are into a better understanding about the definition?
Yeah, that is a good question. And I definitely struggle a lot because all of these terms are so poorly defined. And you'll see I even, I try to stick to intelligibility, but sometimes I slip up and say interpretability. I kind of use these interchangeably myself. So one kind of framework for thinking about this that I like is one that was proposed by the European Union high-level experts group on artificial intelligence. And they proposed this definition of transparency as something that has three components. So the first component of transparency is what they call traceability, which basically means documenting everything you need to know about the what went into a model and the process behind it and all of this. I kind of think of this as like a team who's building a model being transparent with themselves. So I think of something like data sheets also as falling into this category. The second component of transparency that they talk about is communication. So this is things like explaining the capabilities and limitations of your system to end users or to the public or to others on the outside. And the third component that they talk about is what I call intelligibility. And this is making sure that relevant stakeholders understand the technical behavior of a system to whatever extent they need to in order to achieve their goals. More specifically than that, I think it's really hard to define, and even in some ways, I mean, fairness is also very hard to define. I think intelligibility in some ways is even harder because you can't escape the fact that you need to talk about being intelligible like to someone. You can't, I just don't think it even makes sense to think about intelligibility without thinking about who it is that you're trying to be intelligible to. So that just makes it really hard to give any sort of like concrete technical definition. But I find it much more valuable to try to think about defining it in terms of the goals that you have. So you can think about, you know, how much does this model enable people to simulate the predictions? How much does this model help with debugging? All of these types of things. I think you're kind of more likely to get some traction thinking in that direction.
Great, excellent. And there's a question from actually our students asking about, you know, whether you have any recommendations or, you know, suggestions about reviews for state-of-the-art in intelligibility in AI that would, you know, you would actually want to recommend to our colleagues and students.
The question was like review articles about this?
Yes.
Oh, I recommend my book chapter. If you want the human-centered perspective on this. We go into a lot of the methods that have been proposed in machine learning, but also kind of the relevant literature from HCI and from other fields and how these things fit together. In addition to that, there are the 2 papers that I flashed up earlier in my talk. So this one by Beam Kim and Finale Doshi Velez, and one by Zach Lipton. But both of these at this point are probably 3 or so years old, and this field is pretty new and moving quickly. So I think the perspectives have shifted a bit since those were written, but they're still useful.
Thank you. And there's this question, I think, in responsible AI that we didn't get to talk much about today, is that there seems to be a lot of hypes in the media, and there's also you know, hype about AI research in the research community, that, you know, there are always this publicity coming out about claims made for AI. So how do you think we should incentivize the research community to become more responsible in making claims made by, you know, for AI?
That is such a good question. That is something that I've actually been thinking about a huge amount, you know, as the program chair for NeurIPS this coming year, because, you know, the conference last year kind of made some first attempts at going in the direction of encouraging authors of machine learning papers to be more responsible in the way that they're reporting results by adding this requirement that papers include a broader impact statement. People had very mixed reactions to this, but we're currently kind of in the process of thinking about what this should look like going forward, because I believe very much that something in this spirit needs to exist. But the question is kind of what information do we want to be encouraging authors to report, and how do we actually get authors of machine learning papers in the right mindset to think about this? But you know, other communities outside of machine learning are much better about like having a limitations section in their paper. Like it would be very hard in Chi, where I've just started publishing in the past couple of years, to get a paper published without having a limitations section that goes like in explicit detail about all of the limitations of your work. And somehow like in the machine learning community, that's just not a thing. Like we just sell everything, and it's like seen as a weakness to talk about the limitations of your work. And I think we need a little bit of a culture shift there. And this is answering, I guess, like a slightly different question, because I think the question was focused more on the media, which I think is also an issue. But I think just as a community, we need to be a lot more upfront about limitations.
Thank you. So I think I've gone through a dozen questions, and there are a lot of interesting discussions, but just want to, and it's been half an hour, so just want to give the audience a last call for questions.
These are great questions so far. Very exciting.
I have one more question regarding the human subject studies. So there are multiple human subject studies that you've conducted. In the first one, there's this very interesting observations of information overloading. So more transparency on the inner working of the models are actually can sometimes be harmful. So that's a very striking finding. So when I saw that, I was when I saw that example, I was thinking that those 8 feature one will certainly be the most interpretable one, like obviously, but the results turn out to be different. So I was wondering whether you guys have investigated the underlying reasons behind humans' reactions to the model's prediction, because like if I was shown those predictions that's based on only 2 features and completely ignoring all the other features, I would perhaps think that the model is being too simple. So that it risks underfitting and it won't trust it because it's not giving me accurate predictions. On the other hand, if I have more features, more features being used, I see some of the things being suspicious, I would also consider the risk of overfitting of this model to the data. So the underlying reasons behind like people's distrust of the model might sometimes be different. Like, is this a linear relationship, or did you guys control for like the reasons?
That's a really good question. And, there's only so much that we can say about the reasoning behind all of this, because, anything that we didn't specifically like randomize or control for, it would just be speculation. In terms of why I said that I think that this is due to information overload, that is something that we did explicitly explore. So in particular, we were seeing that when we exposed the internals of a model, people were less likely to notice some weird examples that we threw in where the model was making a big mistake compared with when we just gave them the black box model. So we ran a study that was specifically trying to get at some of the reasoning behind that. And one thing we did there was we had a randomized condition in which when we showed people these weird examples, we kind of explicitly had a little like warning pop up on the screen that said, hey, notice that this apartment has more bathrooms than bedrooms. This is a little unusual. And when we actually gave people this explicit, what we call outlier focus, to kind of bring their attention to the fact that this data point is an outlier, then we saw this difference between behavior with the kind of clear internals versus the black box model. We saw the differences disappear. So this is our reasoning for why we think it's information overload, because when we don't kind of explicitly point out the weirdness of the apartment to people, we do see these differences. When we do draw their attention towards it, the differences disappear.
I see. That's a very interesting finding. Yeah, the last point is about the I think the third human subject study about you showing them the results and asking them to tell you whether they think it makes sense, and I think that has something to do with a human's view of uncertainty. I think I've read somewhere that people are very good at gauging uncertainty and somehow quantifying like not 100% type prediction. So if there is a model that tells you that this is the case, they may well just side with that. Is this related to the human random output complexity? I saw this study that give random words to human subjects and asking them to judge whether these text random generated words are coming from like an article or a story, and people can like come up with more positive answers than it should be because it's completely random. Like is it somehow related to like our way of making things up and believing that the pattern exists when actually isn't any patterns?
That is a good question. I don't know, but I suspect, we're definitely seeing a lot of behavior that's consistent with people just trying to make up a pattern that's consistent with what they're seeing in the data and kind of like tell some story around it. So for example, you know, in this case where we had played with the data so that this model had a weird spike at age 38, we had a couple of cases of people who came up with these like quite elaborate stories about why you would definitely expect to see this kind of bump at age 38, which, you know, they're completely fabricated. They were not based on anything at all, but people are good at making up elaborate stories to justify the data that they're seeing. But we haven't explored those questions in any detail.
All right. Yeah. Thank you very much again for the great talk. Yeah.
Thank you. Thank you, Yutong. I mean, I just have one last question because I found the last discussion was quite interesting because for neural networks, right? So deep learning systems are actually very good at learning this spurious statistical patterns between your outcome and your input. So sometimes, you know, your task is A, but then the deep learning systems actually learn the other thing, right? To, for example, actually learn the sampling bias, actually learn which domain you sample it from and how that actually correlates with the label. And then using that to actually give you very good performance. But I'm just curious whether there are some similarity, right, between what Yuxiang just talked about, you know, humans' perception, humans, you know, correlation of the data of some of the unwanted pattern comparing to, let's say, machine learning system, right, where we actually, you know, try not to actually have this machine learning systems, you know, actually correlate this unwanted pattern between the Y and the X in your particular problem. So I'm curious whether you have any thoughts about the role of people, right, actually in this, you know, issues that I just mentioned in deep learning systems.
That is a good question too. I don't know. I need to think about that more, but there's a lot to think about here. I think, yeah, I think there are some interesting connections.
Yes, yes. We do have the, you know, a mind and machine intelligence initiative, which is another initiative on campus that we've been also thinking about other things along this line, and, you know, how do human actually process information and how do machines process information. I think there are certainly a lot of differences, but also some similarity. Okay, great, excellent. Yeah. So I think I spent a lot of time you know, asking Jenn questions, but I do really want to say thank you for taking this time. Usually around this time, I would physically present you a token of appreciation, but this time we couldn't do that. So I asked Laura to actually mail you a plaque. So hopefully that's okay with you. But again, I want to thank you for your time and for this very enlightening afternoon with us virtually. And like I said, you know, I would certainly hope to invite you to visit us on campus after the pandemic is over. So thank you again, Jenn, and thanks everyone for joining us for the distinguished lecture today.
Thank you so much for having me, and I do hope that I will be able to visit in person one day.
Okay, thank you.